SQL, which was the standard language for database processing on relational databases, has also evolved along with the evolution of MapReduce as a programming paradigm. SQL by itself is difficult to compile directly into MapReduce, and a more finer level of programming is required to get reasonable efficiency. There are two languages which are popular in this regard. There is Pig, which came out of Yahoo, and Hive, which came out of Facebook. Each of these is a form of SQL primitives, but executed procedurally rather than in a single functional statement. So for example, if one were to do the calculation that we did last week using MapReduce, that is first trying to figure out the sales and cities that match for a particular address ID by joining the sale and city tables on address, and then joining the result on the city to essentially get sales by city. This is how Pig and Hive make this programming a little bit easier. So the co-group command in Pig is essentially a MapReduce join. The generate for each construct is essentially a map construct, which essentially deals with the output of the first join and creates what the keys are. And then again, there's a second MapReduce, which is done by grouping on city, and then the for each generates what the output one wants, what is the reduce. So essentially, without going into great detail, what Pig does is it takes these statements and compiles them into a MapReduce program. Hive is sort of similar. It's a little bit closer to SQL, where you can actually do a select statement with a limited form of join, and a similar kind of select statement for the second join. Both of these are quite popular now. Pig has one advantage, that it works directly on the distributed file system HDFS if one wants to, or it can also work with HBase. Hive, on the other hand, requires data to be stored in its own format on top of HDFS, so it has its own database rather than an HBase, and cannot work directly on flat files. But both of these have become reasonably popular for coding MapReduce programs as opposed to writing map and reduce functions in a programming language like Python or Java, the way you did in your assignment. Another direction where SQL is evolving is to introduce statistical primitives within the database itself. One example of this is the madlib library, which works on the Greenplum big data database, and this work is emanated from University of California at Berkeley. I'll illustrate madlib with a simple example, which you can see directly on the website for madlib, and this is essentially taken from there. Suppose one has training data, just as we discussed last week, training for a Bayesian classifier. We have attributes which take values, 1, 2, 3, 1, 2, 1, etc. And there are classes, yes, maybe, no, maybe positive sentiment, negative sentiment, whatever. And one wants to create a classifier. Well, the way we did it last week, one would have to compute this using programs, maybe using MapReduce. But in madlib, we can create a classifier using extensions to SQL itself. So suppose we want to create a classifier using this training set and classify in the end these two new samples which are present in another table called toClassify. This is how one does it. You first do a preparation statement where essentially one is computing the likelihood values from the training set and the prior probabilities. next one actually creates the classification using the toClassify table that one wants to classify, and that returns the actual classification. So it's internally created a naive Bayes classifier. If one wants more details, one can actually figure out what the likelihood values were. So one finds that for the first element in the toClassify table, we had a 0.4 chance of a 1 and a 0.6 chance of a 2, and that's why it was classified as 2. Whereas the second one, we had a 0.75 chance of a 1 and a 0.25 chance of a 2, and therefore it was classified as 2. We haven't gone into the details of the syntax, but I guess the idea is clear. There are similar primitives, for example, for computing regressions and other types of machine learning, which we'll study in the following lecture after this one. But this is one direction in which databases are evolving to try to include within SQL some statistical or machine learning primitives. Next, MapReduce is also evolving, and the main element that one needs to add to MapReduce is iteration. Essentially, many applications require one to apply MapReduce again and again. Continuous PageRank calculations is one example. Continuously updating an index is another. Continuous machine learning by updating the training set with fresh values and corrections is a third, and there are many such examples. Of course, there are many ways of iterating. Simplest is simply to run MapReduce again and again, but the trouble with that is that every time one is writing to the distributed file system, which is costly. So there have been some attempts at trying to make this approach of iterating MapReduce directly more efficient by essentially avoiding the data copy and pipelining the output of the reducers directly into the map phase of the next iteration of MapReduce. Another example of iteration is generalizing the MapReduce paradigm to a general data flow graph where map and reduce are simply two types of operations, and one can have a general directed graph of such tasks, and data can flow across such a graph. The key feature that is important here is that tasks block just like map and reduce tasks, so that one map task needs to process all its data before moving on. And that's critical for fault tolerance, as we've seen in MapReduce. If a mapper fails, one can simply restart the mapper with whatever data it was given, simply because it hasn't written anything. So blocking tasks are essential for fault tolerance. An example of such data flow systems is the Dryad link system from Microsoft, the Hyrax research project, and a few others. Lastly, there are implementations of recursion directly in MapReduce, and here the challenge is how to recover if tasks which are now no longer blocking because you're doing iteration using recursion, and recursion requires every step to essentially produce an output, otherwise the next recursion cannot begin. So how does one recover from non-blocking tasks failing? There are two main models here. There's a graph-based model, which is exemplified by Praegle and Giraffe, and there's a stream model, which is exemplified by S4. We're not going to go into details of these in this course. We just don't have the time. But for those graduate students amongst you looking for research work in MapReduce, these are three essential areas where essential ways which iteration is being made more efficient in MapReduce and are promising areas for doing fresh research.